Hello everyone, welcome to my talk. Today I will introduce you my recent research project about infinite interacting particle system on continual configuration space. So let's talk about its background. Its main background is to study the difference of definition of Brownian motion from physical viewpoint and the mathematical viewpoint. So in physical, we know Brownian motion is a trajectory of small particles, and for the small particles, they have collision, they have interaction. But from the viewpoint of mathematical, Brownian motion is a continuous stochastic processes with stationary independent increments. So what is the difference between the two, and what is the gap between the two viewpoints? So so this is a very interesting question, and there exist many models to explain the gap between them. Here I just give you some examples. For example, random walk on random conductance, simple symmetric exclusion processes, and Husfield models. We can write down many other models. But for example, here the Husfield model, it says, in my opinion, this is the model most close to that one of physics. So it says every particle evolves following Newton's law, and they have collision. And when we take the scale of particle goes to 0, and in the diluted region, we will see a target particle converges to the Brownian motion for its trajectory. So we would like to study a similar problem in continual configuration space. So what it is, informally speaking, it is we give ourselves some particle and let everyone evolves as a Brownian motion, as a diffusion. So the interaction comes from the diffusion matrix, and it will use the information of the configuration. So more rigorously, this is a model introduced by Albavio, Cotrati, and Rockner in the paper Analysis and Geometry on Configuration Space. They use point processors as the configuration of the particle, and for the initial probability, it's sampled as Poisson point procedures with density rho. So this is a space very different from the Euclidean space. However, we can also define the functions and the derivative on this space. For example, what is the derivative for the functions on this space? It is we let, for example, x is a position of particle, and we let this particle participate in the direction ek, and then we calculate the rate of change. It gives us the partial derivative. By the similar idea, we can define the gradient, and for the function space, it's a little more complicated. For example, the function space CC infinite on configuration space, it says the function only uses the information in a compact Fourier set. And once we fix the number of particles, we do projection of the function. It is infinitely continuous with respect to every coordinate. We can also define the Sobolev space as a closure of the function CC infinite for the norm of L2 and the L2 of this gradient. So one may wonder if the function CC infinite exists. Here I give you an example. It's called finitely based function. It's nothing but just the composition of function CC infinite in Euclidean space and the linear functional. For this function, we can calculate exactly the derivative. here we define the diffusion matrix. It satisfies several properties. It is local. It uses only the information in a small ball. It is symmetric, and it satisfies uniform ellipticity. And the value at position x is defined by the translation, so it is stationary. Generally speaking, it is the diffusion matrix at position x is we fix a point, we draw a ball of diameter of radius 1, and we look at the configuration in this ball, and we determine the value of diffusion matrix. With all this notation, we can define the diffusion of the processes using the Dirichlet form. Since we now define the diffusion matrix, we define the Sobolev norm, and with the Dirichlet form, we can define Markov processes. It is a very classical theory, and the semi-group is characterized by a parabolic equation. And we remark here our parabolic equation is of infinite dimension. So our main theorem looks very similar to the famous results of John Nash. It says the decay of the decay of variance for the solution of a parabolic equation. Here we give our initial condition is which is a function of a compact support in a cube of size Lu, and we get the decay of heat kernel type t powers minus d over 2. The only difference is here we have a logarithm correction, and for the technical difficulty, we do not know how to remove this term. So this system is very complicated, and how can we know it is our result is correct? So here I give you a solvable example. In the case the diffusion matrix is constant, that is the case every particle evolves as a Brownian motion, and every particle are independent. And secondly, we have to use the initial condition as a linear functional. So in this case, every function can be calculated explicitly, and the variance can also be calculated thanks to the formula of Poisson point processes. And now we can compare the value of variance using the standard heat kernel estimate. But I remark it is the only example I can calculate the value explicitly. And in this example, we see our scaling, our speed over decay is correct. So we talk about some idea of our proof. The main technical of the proof comes from a discrete zero range model, which is proved by Javarez, Landim, Quester, and Yao about 20 years earlier. And our contribution is a generalization from discrete configuration to continual configuration. But I remark our model is without gradient conditions, so it is more difficult, and there are still some steps to explore in this direction. And we get the correct scaling exponent, which is not given in the previous work. And we also fix a small error in the original proof. And we also prove a localization inequality, which is here in the next slide. So the localization inequality, what it says. So we know for diffusion, the typical scale is square root of t. So we want to know if we can get good approximation of conditional expectation if we take a scale much larger than square root of t. The answer is yes. For example, for these results, we know if we take a scale like gamma log t square root of t, so we can get an approximation of the solution by conditional expectation with polynomial speed of convergence. And the proof of this results in continual configuration space is much more difficult and much more technical compared to discrete case, and we have to use some regularization steps. Okay, that is all I would like to tell you about my project. If you want to know all more details, please come to the poster session and look for the poster for the same title. And I will also be online discussion, and you can also see more details in the archive version of my paper. So thank you for your attention.